Today, folks, we're going to talk about fat and how that's going to be metabolized and used by the body, specifically mostly in the guise of exercise. Now, when we're exercising, we are getting fat from a variety of sources. One being the actual fat that happens to be inside of the very low density lipoproteins inside of our bloodstream. We're also getting it from free fatty acids that are going to be being released from our fat cells, our adipose cells, and that's going to, when breaking down those triglycerides, give us both free fatty acids and glycerol. Now, glycerol can be used in the muscle for energy, or it can also go to the liver, where it can undergo gluconeogenesis and then be turned into new glucose, which will then in turn go into the blood and be utilized for energy. Now, we also store fat inside of the muscle. That's our intramuscular triglycerides, the IMTG you see on the figure on the left. Those are then broken down to their individual fatty acids, which will then be broken down in aerobic beta oxidation metabolism inside of the mitochondria. So our final product is going to be ATP and carbon dioxide. Now, if we look at the availability of different types of energy substrates in the body, we can see on the right that we have a massively higher amount of energy stored as fat, not just in the body in general, but literally inside of our muscles. So it's a great choice for energy when we're at moderate to low intensity exercise. Now, as we're going to go up in our exercise intensity, we are not going to be able to free up fatty acids fast enough or metabolize them quick enough when it comes to things like carbohydrates. Now, some of our limits is hormones. Epinephrine is what's going to activate hormone-sensitive lipase, which is going to free up those fatty acids and glycerol inside of our fat cells and put it into the bloodstream so it can then be utilized for energy in our cells. Notice that those free fatty acids are also going to bind to albumin, that's the ALB, and that's going to help transport it around the blood also. That's that plasma lipoprotein. Okay, or so that's aside from our LDL, VLDL, HDL variety. Now, insulin is going to work against that, so it's actually going to stop us from being able to break it down and utilize it for energy. Now, when it comes to getting those fatty acids into our cells themselves, now we need to have transporters and be able to snare those VLDLs, LDLs, and HDLs. And that's simply put not as rapid as simply going through transporters like we're going to find with glucose. Now, you do have also transporters for long chain fatty acids, and medium chain fatty acids can go right through our phospholipid bilayer. But at the end of the day, it's just not able to go as fast as carbohydrate metabolism. Now, we're then limited on literally how fast we can get those fatty acids in the cell. So if we see on the right, we can see how glucose just goes straight for GLUT4, goes through glycolysis. We've got pyruvate, and then pyruvate can hop right into the citric acid cycle. Now, fatty acids, depending on their size, are going to use two different transporters, or those medium or short chain fatty acids can go straight through the phospholipid bilayer. At that point, they then are going to be at the mercy of hormone-sensitive lipase and need to be bound to carnitine so it can go through the carnitine transferase to get into the mitochondria. Now, our intramuscular triglycerols, if we look at our picture on the left, you can see how it is literally right next to the mitochondria. That's the MI. And then you see the little black granules, that's actually glycogen. That's going to be obviously broken down for energy. Then we finally have beta oxidation, which is going to happen in the mitochondria. It's a four-step process, but it has to happen for every single two acetyl-CoA we're pulling out. So that's going to, again, take some time to go through. Now, that transportation into the mitochondria through carnitine shuttling, if you notice, goes through our CPT1 and CPT2 transfer proteins, which are going to bind that fatty acid from outside of the cell and then transfer it through the intermembrane space and then bring it into the mitochondrial matrix. Now, obviously, carnitine can be a limiting factor, and that's why you see carnitine itself is a supplement that some individuals are going to use with the hopes that it's going to be able to improve their performance. And then on the left, we have beta oxidation, where every round only gets us 2 carbons at a time. So it, in effect, requires a multitude of rounds per individual fatty acid, which can obviously be a bit of a limiting factor. Now, when it comes to fats as fuels, when it comes to exercise, from rest to moderate intensity, we're going to be utilizing a lot of fat for fuel. So if you look on the bottom left, we can see literally the rate of which we're breaking down fats given the percentage of our VO2 max. And as we go up above about 65%, we're going to see the total amount of fat we're breaking down going down. Now, this isn't necessarily an issue with how much fat we have freed up, because if you notice on the right, our amount of fatty acids in the blood and the fat oxidation rate, even when individuals were given far higher amounts of fatty acids, they still weren't able to metabolize as much fat as they were in a control condition, which means it's not the actual availability in the blood, it's more of the ability of the body to preferentially use glucose, along with limitations on transporting into the muscle. Now, if we look at the figure in the upright, we can actually see the contributions of the muscle glycogen, the fats inside of the muscle, the fat in the bloodstream, and the glucose in the bloodstream. And we'll notice as we're going from low intensity to higher intensity, we're going to start off utilizing mostly fat, but the fat that's actually in the bloodstream, and then slowly with time, we're going to be upticking both our use of the intramuscular fat stores, but definitely the intramuscular glycogen stores. So as we go up in intensity, we're utilizing less and less fat. Fat's a great long-term fuel source, but not a good slow source of energy. Now, in order to get those fatty acids into the cell, medium chain and short chain fatty acids are going to be able to go straight through the phospholipid bilayer. Meanwhile, long chain fatty acids have to go through transporters. Now, if we look at the bottom and we see the rate of radio-labeled fatty acids and how much of them are going to be metabolized in a fasted state compared to a carbohydrate supplemented state, we notice that the long chain fatty acids goes way down, and that's because of the preferential transportation of glucose into muscles. Meanwhile, notice there's not a lot of change in the amount of medium chain fatty acids that are broken down, because notice they also won't have to use the carnitine shuttle to get into the cell. Now, as we become more and more well-trained, we are going to be able to utilize a little bit more fats as fuel at rest, and perhaps get a little bit more out of them at highest intensity exercise. But at the end of the day, there's not a big difference in the amount of fat you're going to be metabolizing, except for the influences we're going to find from the diet itself, which is if we happen to be utilizing more carbohydrates in our diet, we're going to be utilizing more carbohydrates during exercise, and vice versa. Now, the regulation of this is sometimes referred to as the Randall cycle, where we're going to see giving different feedback loops, and that's where we have positive and negative connotations, where if we happen to be having a much higher amount of energy that's required, so that's a lower energy state, along with having a greater decrease in pH, we are going to be focusing on utilizing glucose metabolism more so than we are going to be utilizing fat metabolism. Now, obviously, epinephrine is going to help us utilize more fat than we would have otherwise, but if you notice with that pH dropping, that's the big key of it's going to inhibit it, specifically when we're having to tap more into anaerobic metabolism, because we're still trying to get both the products of fat, beta oxidation, and glucose through glycolysis products to go through the citric acid cycle, and we can only get so many acetyl-CoA through at a time. So the body's going to preferentially choose whichever happens to be the one it can produce at a much higher rate. Now, what we do notice is that if we give people fats as a fuel, and that's once again relating to what their diet was recently, it's actually going to help preserve intramuscular glycogen to a certain extent. Like you would expect, if you have more fuel available, you're going to utilize that available fuel and then tap into your stores only when it's necessary. And that's a great thing because obviously it can have a glycogen sparing effect. Now, for maximal performance, we still want to go and supplement with carbohydrates, but if all you have available to you is fats, then by all means, make it happen. Now, when it comes to supplementing with these and increasing exercise, fats don't really seem to have any positive effects so far in really increasing acute performance. Maybe medium chain triglycerides, because they don't have to use a transporter, and potentially ketone bodies are going to help enhance your performance in aerobic bouts, but overall, most of fat supplementation, such as taking in omega-3s through fish oil, the real efficacy behind it is long-term supplementation and supplementation to help enhance recovery from bouts of exercise, from disease, from injury, from illness. Now, how does a diet with a certain amount of fat modify our performance? Well, we can tell you that in studies where you have somebody that's fasting, turns out you're going to start to develop ketone bodies, and you're going to have to utilize fat more as a fuel, but that overall is going to cause a decrease in performance. Now, if we just happen to give someone a high carbohydrate diet and compare it to a high fat diet, when it comes to aerobic performance, we're going to see a greater performance from the individuals in the carbohydrates. Now, if we compare a normal diet to a high fat diet, which really means we gave them more carbs, and we look at exercise to fatigue, you're going to see potentially an increase in performance thanks to having that higher fat intake if you didn't increase your calories in general. So it's still kind of boiling down to those calories in and calories out, along with our own predispositions to certain types of fuels depending on whatever exercise we're doing. Now, keep in mind, if you're not an aerobic athlete, it doesn't make that big of a difference. Because at the end of the day, we're really talking about how long of a duration are you trying to perform for, and once we know how long you're trying to perform for, trying to match that to the total amount of caloric demand you're going to have for that given exercise. Now, the final one I'm going to leave you with is understanding cholesterol and a basic concept of what ketone bodies are. Now, when it comes to all of our steroid hormones are based on cholesterol. That cholesterol is then going to be modified into estrogen, cortisol, testosterone, etc. So we do need a certain amount of cholesterol in the diet, and or we actually create our own cholesterol from essentially our fatty acid intake. Now, some people have genetic predispositions to where their cholesterol intake really does massively increase their blood cholesterol level, but most people, their cholesterol intake will not change their blood cholesterol much or so much at all. Remember, cholesterol or steroid hormones are going to be utilizing signaling directly onto the nucleus of the cell, causing changes in the DNA expression, along with, we can tell you that the amount of omega-3 to omega-6 fatty acid intake is going to influence how much cholesterol you're going to have. Now, cholesterol itself actually helps give your cell membranes a certain amount of integrity. If we decrease our cholesterol levels too low, and that's usually what happens from using drugs like statins that lower cholesterol levels, our cells can become too fluid, and because of that, they're far more likely to fall apart. And if they obviously fall apart, that's a bad thing, because that means they've literally broken down inside of you, and you could have that sudden muscle pain or weakness they talk about, which means you're probably not going to live too long. On the other side, we then have ketone bodies. Now, ketones are going to be made from partial metabolism of fatty acids. So notice when we look at beta oxidation, you get your 2-acetyl-CoA. Well, then we can go through a couple different modifications through enzymes to get to our three major different types of ketone bodies: acetone, acetoacetate, and beta-hydroxybutyrate. Now, beta-hydroxybutyrate has been shown to have potentially a number of positive effects on potentially aerobic performance, but also just general overall health, it seems. Hence why the ketogenic diet, for some people, can be very useful. Now, notice acetone is typically referred to as nail polish remover, so you don't necessarily want to have a lot of that floating around inside of your body, so you will have modifications either way, and that's why some people really do not tolerate a ketogenic diet very well. It's important to understand that there are some very, very interesting applications of this diet in certain disease states, but this is not a panacea, and it's not as good as some people say it is, but it's also not as bad as others will go ahead and talk against it. Whenever we go ahead and meet and have a conversation about fat metabolism and fat supplementation, we're going to make sure that we have a conversation about ketones and the ketogenic diet. Thanks for listening, guys. Have a great day.